Alright, so today we're going to be talking about number sense, and that is going to include our rational numbers, our rational number operations, and then we're going to talk, and probably another video, about equivalent expressions, equations, and inequalities where we're applying that number sense. So what are rational numbers? And rational numbers we've talked about as anything that can be written as a fraction. So this includes negative and positive numbers as well as decimals and percents. And the only numbers that are not rational numbers are called irrational numbers. And an example of an irrational number is pi, and you know we've seen pi before, and it's just a decimal that keeps going. It doesn't terminate, it doesn't repeat, and in any pattern. So what we have done here is some examples of rational numbers. I can write it as a fraction as long as b isn't 0. 5 is a rational number. I can write that as a fraction of 5 over 1. Negative 1 and 2/5. Same thing, I can write as negative 7/5. 25/100 I can write as 1/4. And here's an example of one where we have repeating the fraction 2/3, which is the repeating decimal 0.6 or 6/10, and then it just keeps repeating. You can also see over here in this little diagram, we've got the natural numbers that you've worked with since kindergarten, the counting numbers, whole numbers, which is the natural numbers per 0, and it's like the nesting dolls that we talked about in class. Integers then are just those whole numbers and natural numbers and their opposites. And rational numbers is when we add in those fractions and decimals. So rules for adding and subtracting fractions. This is something you guys have been doing for a while. When I'm adding and subtracting fractions, I just have to make sure I have a common denominator. And it's important to note that when we make that common denominator, I'm not coming up with a new number. It's actually just an equivalent fraction of the original one that we had. I'm just making it so that I'm working and adding together the same size parts. So in our example here we have 3/4 plus 1/8, and I see that I can multiply 4 by something to get to 8, and I'm like, oh, that's 2. So if I multiply the denominator by 2, whatever I do at the bottom, I always have to do the top in these cases. So if I multiply the denominator by 2, I'm going to multiply the numerator by 2 as well. And so I get my equivalent fraction of 3/4 is 6/8. Now that they have the same denominator, I can add those together. And 6/8 plus 1/8, I've done all that work to find that common denominator. I'm going to keep it. I'm still using those same size pieces, but 6 plus 1, I now know that I have 7 of those pieces. When I multiply and divide fractions, however, I do not need to do that. I'm just going to multiply. When I'm multiplying fractions, I multiply straight across like a ninja. Top by the top, bottom by the bottom, or numerator times numerator, denominator times denominator. So for instance, 2/5 times 6/7, I go straight across the numerator, 2 times 6, and get 12. And with the denominator, I do 5 times 7 and get 35. Now the last thing I always want to ask myself at the end of a problem is, can I reduce that? And a lot of times you can see if we're doing multiplication, we can always cross-reduce before we multiply. In this case, there's nothing that 12 and 35 have in common, so I cannot reduce that. But in our second example, 1/4 times 2/3, I could multiply the 1 times 2 and get 2, and the 4 times 3 and get 12, which reduces to 1/6. And I do that by dividing both the top and the bottom by 2. And as long as I can divide the top and the bottom by the same amount, I once again end up with an equivalent fraction. Now I could do this ahead of time. I could do what we call pre-reducing in my class, and I could see that I can cross-reduce before I multiply, and I could have divided this by 2 and gotten 1, and I could have divided 4 by 2 and gotten 2, and then I would have had 1 times 1, which gives me 1, and 2 times 3, which gives me 6. When I divide, it's very similar, only I'm sure that you remember the keep change flip moniker that you've used in 5th grade, and in 7th grade we start calling it keep change reciprocal. I want the reciprocal of that second number, so I'm going to keep the first number, which was 2/5. So 2/5 divided by 1/3, I'm keeping the 2/5. My division is changing into multiplication, and I'm going to take the reciprocal, which is the flip or inverse of 2/3, which is 3/2. And I'm going to multiply across, and then I'm going to reduce. So 2 times 3 is 6, 5 times 2 is 10, and then I'm going to divide again by 2 on both the top and the bottom to reduce. And there are different numbers that you can divide by. It doesn't necessarily have to be 2. We also have down here 4/7 divided by 2, and it's important to note here that they kind of skip this little step, but you have to think of 2. I can write that as 2 over 1. I can turn any whole number into a fraction by putting a 1 in the denominator. And so that's what they have done, and that's how they then went from here and did the keep change reciprocal. And that 2 over 1 becomes 1/2. Once again, with both of these division examples, I could have divided and reduced before I did the work to find my answer, or I can always reduce at the end. If I want to convert then between fractions and decimals and percents, there's some simple rules to follow for that. When I am going from a fraction to a decimal, all I need to do is divide the numerator by the denominator. And so I'm going to demonstrate that over here with 3/4. My numerator always goes inside, my denominator goes outside the house. I know that I cannot get a whole 4 into 3, so I'm going to go ahead and add decimal and at least 2 zeros. If I add extra zeros, I just don't use them, not a problem. 4 can't go into 3 like we said. Bring my decimal point right up to where, right above. Lining up things when I'm doing this, lining up my numbers and my decimal points is always very important. Then I ask myself how many 4s can I get into 30, or how many times can 30 be divided by 4? And that is 7 times. 7 times 4 is 28. 30 minus 28 is 2, and then I bring down the 0. Then I ask myself again, how many times can 4 go into 20? Well, that's 5. 5 times 4 is 20. I subtract. I have nothing remaining, so I don't need to add any zeros, and this is an example of a decimal that terminates or stops. I've come down here, I have a remainder of 0, and I'm done. I can then take this decimal to turn it into a percentage, and I'm just going to multiply it times 100. So when I take 75 hundredths and I multiply it times 100, all that's going to happen is my decimal point is going to move 2 places to the right. And so that gives me the percent, 75%. 2/3 as an example, I'm going to do 2 divided by 3. I'm going to add my zeros again. 3 cannot go into 2. Bring that decimal up. 3 can go into 26 times. 6 times 3 is 18. 20 minus 18 is 2, and I bring down the 0. Now I'm going to notice right away that I started with 20 here, and now I'm suddenly going into 20 again, which means I'm going to be able to go into it 6 times again. 6 times 3 is 18 again. 20 minus 18 is 2 again. And this becomes a pattern, and this is what we call repeating. And I can stop right here and put the bar over there, just over the first 6, or I can put it over both of them. When I go to turn this into a percent, it would be 66.6% repeating. A lot of times people will round that to 67%, and that's an approximation. If I start with a percentage or a decimal, if I start with 50%, I'm going backwards to a decimal. I'm going to divide this by 100. So 50 divided by 100 is going to take my decimal point. I'm going to do this right here. 50 divided by 100. I'm going to take my decimal. It's going to move my decimal point back to the left 2 places this time because I'm dividing, which is how I got my 50 hundredths or 5 tenths. And I can take this and I can think of this either way as 50 hundredths and 5 tenths. And when I go to make this into a fraction, I'm going to look at what place value that's in. That's going to end up being my numerator. So if I think of it as 50 hundredths, that would be 50 over 100. And then I need to make sure I reduce that. Well, there's a 0 buddy in the top and the bottom here. So when I'm dividing, I can go ahead and get rid of those extra zeros. Now I have 5 over 10. I can divide both of those by 5 and find out that my reduced fraction is 1/2. We have some rules for adding negative numbers. And if both numbers have the same sign when we are adding with positive or negative, I simply add their absolute values, and then I keep the sign. So I'm sure that you're familiar with 4 plus 6, and you know that that is 10. Well, they were both positive. The absolute value of 4 is 4, the absolute value of 6 is 6, and 4 plus 6 is 10. And they're both positive, so I keep the positive sign. If I had -4 and -6, once again, they are both the same sign, so they are both negative. So the absolute value of 4, well, it is 4 spaces away from 0, so that would be 4, and -6 is 6 spaces from 0, so that would be 6. So 4 plus 6 again gives me 10, and in this case it was negative, so it's a -10. I can also do this with rational numbers. If I had 3/4 plus 2/4, I would just add them and get 5/4, or I could also say that that is 1 1/4, and it's all positive, and I just add it together. If it was a -3/4 plus a -2/4, I can do the same thing. I'm going to add these two numbers together. They have the same sign, so their absolute values are going to be the same as their positive counterparts. So I get -5/4, or -1 1/4. And the biggest error I see people make is that when they go from this improper fraction to this mixed number is that they lose that negative sign. If they don't have the same sign, say I had 4 plus -6, I have to look again at their absolute value, and the absolute value of 4 is 4, and the absolute value of 6, -6 rather, is 6. So I have 4 and 6. Since I have opposite signs, in other words, they do not have the same sign, I'm actually going to subtract those absolute values. So the absolute value of 4, and you'll see that with bars like that, is 4. The absolute value of -6 is 6. And I'm going to do 6 minus 4, and I get 2. I go back and I look, which one of these had the larger absolute value? Well, 6 is a larger absolute value, and since 6 was negative, that means that my answer is a negative. Another way you can think of this is I have 4 positives and 6 negatives, and a negative and a positive cancel each other out. So I can get rid of 1 from each side, going back and forth, while I end up with 2 negatives. So that's another way you can work your way through it. Once again, I can do the same thing if I have rational numbers or I have fractions or decimals involved. So say I had 10 plus -30 hundredths. Once again, I'm going to take their absolute value. So I've got 10 and I've got 30 hundredths. Because they are opposite signs, I'm going to subtract them. And I have to make sure in this case that I line up those decimals when I go to subtract. I'm going to have to borrow over here. And I get 9 70 hundredths, or 9 7/10. When I go back to look at this, 10 had the larger absolute value, and it's positive, so my answer is positive.